Let's start. So, last class we were looking at how to solve problems of trusses, and we looked at the what we call the method of joints. So, let's look at the example again and complete the solution. We had a truss which was of this shape. So, we called it A, B, C, D, E, F. This was the truss where in a truss it is always assumed that each member is joined. Not specified, but let us assume length of each member or length of this dimension is L, and similarly they have the same length. So, all horizontal and vertical members have the same length. This I think I had not specified when I solved this problem. So, we will first solve this problem and we will look at what is called the method of joints. So, first thing, as we said, as we had done last time, was to find, when particularly this will be needed when we use the method of joints. There is a second method we will do called the method of sections, and there, depending on the type of problem, you may not have to find the reactions. Sometimes you may have to. So, first thing what we do here is find the reactions at supports, and in this case the supports are A and F, and we did this in the last class. So, for this we draw the free body diagram. There was one more member which I have not drawn here. There was a member CE also. Obviously, without CE this will not be a truss, or this won't be a properly rigid truss. So, here we have AX, AY, FY. So, this is what we have drawn is the FBD of the full truss. And from here what we get is AY is 1000 newtons, FY is 1000 newtons, AX is 0. Okay. So, having done this, then we move on, we move to a joint which has only two members connected to it. Now, in this case I have two options, either I can move to point A or to point F. That is the joint where there are two members connected. Why do I go to a joint connected to two members to start with? Because I will get only at that joint. Basically, I will draw the free body diagram of the joint and I will solve the equations, because it is a point where all forces are intersecting. So, I will get, for a planar case, only two equations. So, that is why I go to a joint connected to only two members. So, the first thing which I will do here is then move to joint A. So, if I move to joint A, now we show all unknown forces in members as tensile. Now, this is the notation we take You could choose them to be compressive, it doesn't matter. It is option is up to you. But as a rule, as a sort of general this thing, we say unknown forces, we take them as tensile. Now when I go to pin A, on pin A I have, there is a force of 1000 newtons acting like this. In addition to this, I have a force AB and a force AC. These are coming from the two members. Now these here are the forces on the pin. So therefore, force on the member is opposite of this and hence tensile in nature. So the unknown forces which I have, I will put them up as tensile forces. So when I draw the free body diagram of the pin, the member is pulling the pin and the pin will in effect then pull the member. So therefore, a force AB written like this is a tensile force on the member because this is the free body diagram of the pin, not of the member. Is that clear? If it was the free body diagram of the member, then a tensile force would have been in the opposite direction, pulling the member. AB member is like this, it would have to be pulled at A. But this is the free body diagram of the pin. Now on this, I do sigma fx is equal to 0, sigma fy is equal to 0. So when I do, first let's do sigma fy is equal to 0. So what I will get is AC cos 45 plus 1000 is equal to 0, where AC represents the force in member AC along its line of action. The direction is known because these are all two force members. Okay. So now from here what I get is AC is equal to minus 1000 root 2 newtons. Okay. Now what does the minus sign indicate? That means the force in AC is equal to 1000 root 2 newtons compressive. And this is how, if I have to write the answer, I will write the final answer like this. Okay. And then when I work out the force in AB, then I get AC sin 45 plus AB is equal to 0, and this will imply AB is equal to 1000 Newton tensile. AB turns out to be minus AC sin 45. Now AC itself is minus 1000 root 2, so therefore that becomes 1000 Newton. It's positive, so therefore it becomes tensile. So this way I have solved in this truss. When I started with this, I have solved for members AB and AC. Next, I have an option. I will move. I can move from A to either point B or to point C. Which point should I choose? I will choose B. Why? Because on B I have two unknown forces, BE and CE, whereas AB is already known to me. If I go to point C, then I will have three unknown forces there and I will not be able to solve them directly. So therefore, I will move from A to point B. So next, when I move to point B, now let's draw the free body diagram of the pin at B. What do I have? On the pin at B, there is a 1000 Newton force which is acting downwards. This is a part of the problem. Okay. Then we have the pin AB. I know this is 1000 newtons and this is actually AB. Now, if I know a particular force and if I know whether it is tensile or compressive, I will show that force with the correct direction. So, in this case, I do not show it as right tensile or compressive. This is known to me, this is 1000 newtons and this is AB. This is a tensile force, so it will pull the pin. So, I will put it in this direction. Now, next I have two more unknown forces, which are the forces at BC and we have BE. And it is very clear what we have is BC is equal to 1000 newtons and similarly BE is also equal to 1000 newtons, and both these forces being positive are tensile forces. Okay. So, now once again if I go back to the truss, I have now solved for BE and BC. Now, what will I do? I will go to point C, because now on C I know AC, I know AB. So, the next step would be to C. Now, on C what do I have? On C I have AC. Is AC tensile or compressive? AC we saw was compressive. So, therefore, I will show AC and this is 1000 root 2 newtons. Since this is a compressive force, I show it with its right direction because I know AC. Now, the other force which I know is BC, which is tensile. So, therefore, this is 1000 newtons, this is BC, and then I have two more. I have CD and I have CE. Okay. So, now I can work on this. I can now solve for CE and CD, and this way I can find forces in all the members. So, once I have gone to C, I will get these two forces. You can work these out. I am not working out the answers for you. You can work it out for yourself, get this thing, and actually what you will see is this 1000 root 2 newtons, if you see its vertical component, that will be 1000. So, that these two vertical components will cancel out, that means CE will be equal to 0. So, this in fact the way I have written this 1000 newtons is, I will place it correctly. I will place it here. So, this is CE, that is CD, and you will get CE is equal to 0 and you will get CD is equal to minus 1000 newtons. So, when you solve for this, you will get CE is equal to 0 and CD is equal to minus 1000 newtons. So, that means CD will be 1000 newtons compressive, and so on, and you can solve for the whole thing. Okay. So, this is called the method of joints, and as you would see, this is a reasonably, when we look at the method, it is what we can term it as a brute force method for solving the trusses. It is a brute force method, therefore, it is fit to be programmed because you make an algorithm, ask the computer to do things, because you do not have to use too much of your mind, it will keep on solving it joint by joint. Now, as I showed to you in the last class, there are many trusses which are very long, and suppose if you have to find the force in one of the middle members, and if you use the method of joints, that means you have to start from one end and you keep on going till you reach the middle member, and that means it may take you a long time. Is there a smarter way of doing things when you have to find forces in one or two members? So, is there a better method if we have to find forces in say 2 or 3 members of a long truss? And here it turns out that there is a better method, and we call it as the method of sections. And in the method of sections, what we will do is we make an imaginary cut in the truss. So, wherever the cut passes through a member, the internal forces and moments acting there will be exposed. We have seen whenever we cut a body, we can notionally cut any body when we are solving a statics problem, and when we do that, at the cut section we will get an unknown force and an unknown moment. Now, going by the discussion we had for a straight member truss, what do we find when we cut a straight member truss? What sort of forces will be exposed? If we cut a straight force, you are very right, only a tensile or a compressive force in that member will be there. That means we know the direction of the force and there will be no moment. And this is what we exploit in the method of sections. So, therefore, let us write this down. In general, this is what should be exposed, but in a straight member truss, all members are two force members. So, only tensile or compressive force is exposed and no moment. This is very important. So, therefore, when I cut, so for example, let us just see this truss which we had solved for. This was a truss which we have done just now. Suppose if I make a cut like this. So, now this is up to me. In the method of sections, I can make any cut which I feel like. Okay. So, if I make a straight cut like this, now I can draw the free body diagram either of the left side or the right side. So, that is what I will do. I will draw the free body diagram of one of the sides. So, let us say I draw the free body diagram of this is the cut part. Now, at point A, I will show A sub y is equal to 1000 newtons, A sub x was 0. Now, within this, I have to show all the external forces. Now, point B is also within this left part. On point B, 1000 Newton force is acting, so I have to show this. On this, I will not show the forces on point C, or sorry, on point E and point F, because they are not a part of this truss. I have made a cut, so I only show the external forces acting here. In addition to these external forces, so now this was basically point A, this is point B, this is point C. Now there are these three unknown, there are three cuts. So here I will show CD, CE and BE. So at the cut, I have these three forces, a force in the direction of CD, a force in the direction of CE, a force in BE. And all these, as I have shown, they are tensile forces. Because at the cut section, if the force is tensile, it will come out like this, it will pull the member. So all these three have been shown to be tensile forces. These are all three unknown forces. Now, in the method of joints, you realized we did not use the moment equation at all. But in this, I have now three equations to be used. I will use sigma fx is equal to 0, sigma fy is equal to 0, and moments is equal to 0. And moment I can take about any point in space. It need not be a point which is on the cut section itself. So for example, if I take moments about E is equal to 0, what will I get? If I take moments about E is equal to 0, I will get CD in one go. Is that clear? So I will take, in this case, let's write this down. We take moments about E is equal to 0, and this will give me CD just in one equation. Once I get CD, then I can do sigma fx is equal to 0. That will give me a relation between CE and E. Then I do sigma fy is equal to 0, and that will give me, in fact, if I do sigma fy is equal to 0, I would have directly gotten CE. Okay, and then sigma fx is equal to 0 will give me BE. So by making a single cut like this, and I would still have to work out the reaction. AY is equal to 1000 Newton, AX is equal to 0, and after that making a cut will give me these three forces in one go. Just I don't have, so this, see here it is only one point away from the joint, but this could have been a very long truss and this could have been a middle part. So then all I have to do is I have to take this, but now realizing when you take moments about point E, we have to take the moment of AY, and we have to take the moment of 1000 Newtons, and we have to take the moment due to CD. Sometimes you can take moments about 2 points is equal to 0, not just one. Take it about E, then you can take, for example, here if you take moments about C is equal to 0, you will get BE. So now there are 2-3 things we learn here. Firstly, the moment which we take about, the point about which we take moment is equal to 0 need not be a point on the cut truss itself. It can be away from the cut section. It can be any point in space. It could be a point, for example, C is a point on the cut section, E is a point which is not on the cut section. We can still take moments about both these points. That is one thing. Secondly, the cut section which we take, I have right now shown it at the middle, but it could be very close to point C, or it could be very close to point E, or it could be in the middle. So this cut section is a notional section which we are placing, and it could be anywhere. So that also one has to keep in mind, that we can solve these problems and we can get to these things like this. So this is how one works with the method of section. Now in the method of section, of course, the main thing is the smartness with which you choose a section. For example, sometimes you may find in a truss, even if I don't show all these are joints, this is what is termed as a K truss. And suppose if you are asked to find the forces in members 1 and member 2. Okay. With a truss like this, we are asked to find forces in members 1 and 2. Well, you could have a new type of truss. The question you would like to ask me is, how do we find the appropriate section? Well, obviously one guideline is that your section has to be such that the forces which you want to find are exposed in the section. Otherwise, there is no point. So now if you have to find forces in 1 and 2, you have to make a cut where these two are exposed. So therefore, one simple this thing looks like, let us make a straight cut. If I do this, let us see, this is A, this is B, this is C, this is D, this is E. If I make a cut like this, now if you were to solve this, let us assume some external forces are also acting. I have not shown them. If you were to solve this for exam, would you take the left half or the right half? Left. If you draw the free body diagram of the left half, will unknown reactions come? They will. Whereas if I look at the right half, the unknown reactions are not there. Because in the right half, you maybe, let us say, some forces are acting, I have not shown them. So suppose F1, F2, some external loading is there, F3, F4. If I look at the right half now, there are no unknown reactions. So obviously my choice should be to choose the right half, not the left half. Why? Because if I just have to solve this problem, if I use the left half, first I will have to calculate the unknown reactions. Whereas if I use the right half, I don't need to do that. So I'll use the right half. Now if you look at this, what you will realize is, if I take the right half, then the cut will look something like this. This is between this point A, this is point B, this is C, this is E, then we have BA, CD, this is D. This is how we may have more points, it does not matter. This is how these, so now I will have AB, AC, CD, DE. When I take a cut like this, if I take moments about A is equal to 0, I will get a relation between CD and DE. I take moments about D is equal to 0, I will get relation between AB and AC. But I will not be able to solve for both the unknowns AB and AC which I want to find. I have to find forces in 1 and 2, I will not be able to do that. So then what do I do? Sigma fx, sigma fy will not help me because totally there are 4 unknowns and you have only 3 equations. So sigma fx and sigma fy will still give you some relations, but they will not be enough for you to be able to solve. Then what do? You think about it, maybe you can come up with another cut. I will use the blue color for this cut. If I make a second cut like this, now in this cut I have AB, I have BC, I have BE, and here I have CE. Okay. Now in this second cut which I have taken, I take a cut like this. If I take moments about E is equal to 0, then this force and this force, all the 3 will pass through E. So therefore, by taking the second cut and taking moments about E is equal to 0, I will get AB directly. Once I know AB, then I can go to the previous cut and get the value of AC. So this is how sometimes, now the sections for the assignment and in the book, the sections are given to you, but in the exam the section you will have to think for yourself, that will not be given to you. Okay. So we have some homeworks in the truss which we'll start doing this week, but so that we'll look on. So I think this particular truss and this particular cut will also come in the homework. Next, well, this is another example of a problem where you have to find, there is a big truss given like this, there are different type of loadings, there is a pin joint here, there is a roller joint at L, there is 1 kilonewton, 5 kilonewtons, 1 kilonewton. This is how a typical truss problem will look like. And here it says find the forces in members FH, you have to find the force in FH, GH and GI. You have to find the forces in these three members. Okay. So you have to find forces in FH, GH and GI. What is the obvious thing to do? That you will make a cut like this. When you make a cut like this, all these three will be exposed, and then we should think about it. When we make a cut like this, and if I take moments about H, then these two will be there, I will get GI. When I take moments about G, I will get FH, and then I can do sigma Fx or sigma Fy is equal to 0 and get the third force. So notionally this is first thing which I do when I see the problem. I say, okay, I have to make a cut like this. Is that clear? Yes. Once I decide this, then for me, first thing then I'll have to work out, first I'll have to find the reactions and other things and then solve the problem. Because here when I make a cut to the left or to the right, one unknown reaction will come here, one unknown reaction will come here. So those reactions anyway I can't get away with, as in the previous problem I was able to get away. So I can't do that. So the first step will be, as we discussed, we draw the free body diagram of the entire truss, and then if I take, so I have 1 kilonewtons, 5 kilonewtons, 1, 5, 1, 5, 1, 1, all these forces acting here, and I take moments about point A is equal to 0. So I will get the force at L, and you work out the equation. This is a solved problem from the book, I think it's problem 6.3. So when you take moments about point A is equal to 0, you will directly get the force at L, and which turns out to be 7.5 kilonewtons. These moments, I think by now you will be in a position to take moments of all these forces. So we have 5 kilonewton force acting at, these are 6 panels at 5 meters each, so 5 into 6, and then we have 10 into 10 meters into 6 kilonewtons, because we have, in fact, each of these we can replace the 5 and 1 as a single 6 kilonewton force. See, this 1 kilonewton, 5 kilonewtons has been replaced as a single force by 6, because you can push the force along its line of action. So this way we solve, we get the values for the reactions, and once we get the values for the reactions, then we can, then as we said, we make a straight line cut section which cuts FH, GH and GI, because these were the three unknowns we had to find, and then we draw a free body diagram of the cut section. Now here the cut section free body diagram, if you see, has been drawn very close to point H. As I said, we can either draw it very close to point H or to the other end or somewhere in the middle. I had drawn somewhere in the middle, he has drawn the free body diagram just at the pin H. So therefore at pin H, because the pin H is included in the free body diagram, it's just to the right, a 1 kilonewton force at the top, this is an external force, this 1 kilonewton force and this 7.5 kilonewton force, they will come in as external forces. Okay, and then we have the force in FH, the force in the second cable and the force in the third cable, in the third member, force in GH and force in GI, they are there. And to find this, first we take moments about H is equal to 0, that gives us the force in GI. Okay, if it is positive, that means it's tensile, if it is negative, then it will be compressive. Then to complete the problem, well, what he has done is, we move ahead, we take moments about point G is equal to 0. So he's taking moments about point G is equal to 0, and that will give us these two forces pass, so we get force in FH. And once we have this, then we can do sum of forces, we can take moments about L is equal to 0, and then we get the third force, and so on. So, or we could do sigma Fx is equal to 0, sigma Fy is equal to 0. So, it's up to us, we can view and then we can solve for this. Now, there is one more thing which we have in trusses, and this is something about which I would like you to really think about, and this is, there are certain special conditions which come where you can, by just looking at the truss and looking at the loading, predict forces in some members without doing any actual calculations. And the first of these cases, and I will draw this also, is suppose you have a joint with 4 members such that they form 2 collinear pairs. So, I have a joint at point A, let point A is a joint, I have say AB and AC, and I have AD and AE. So, these are the 4, this is a configuration which I have, which was shown in the figure in a more realistic setup like this, that we have a pin here, AE and AC are 2 collinear members, and AD and AB are 2 other collinear members, and there is no other external force acting on the pin. So, with this and no external force on A. Now, here if I look at the direction, so now in fact I have not shown, this should be collinear, AED are collinear, I will just EAD is a straight line, and similarly CAB is also a straight line. Now, if I look at the direction perpendicular to AD and I draw, I say sigma, let us call that as the y direction, and I say sigma Fy is equal to 0, what will I get? So, here if I look at, let us look at the direction, let me call this as y, this is perpendicular to EAD, and here now if I say sigma Fy is equal to 0. So, what I will get is, if this angle is alpha, I will see this will also be alpha, I will get AB cos alpha is equal to AC cos alpha, this will imply AB is equal to AC. Okay? Is that clear? That means the forces in members AB and members AC, they have to be equal. And similarly, when I do a force balance, now having done this, I do a force balance along the x axis, which is along AED or EAD, I will get AE will be equal to AD. So, whenever I have 2 collinear members connected to 2 other collinear members at a pin, then the forces in the 2 collinear members will have to be identical, and the forces in the other 2 collinear members will also be identical. Okay. But if there are 6, then this will not work. This will work only when there are two pairs of collinear members and there is no other external force. If suppose there was an external force of 1000 newtons acting vertically, then this conclusion would not be valid. Is that clear? So this is one situation which we get in trusses. Now suppose you have a, so now this is what, so now what this tells you is that force in the two collinear members are equal and forces in the other collinear member also equal. That is, AB is equal to AC and AE is equal to AD. It does not tell you that AB is equal to AE. In each collinear pair, they will be same. Now, some corollaries from this. Suppose you have a situation like this. You have a truss connection like this. AB and AC are collinear members and they are connected to AD, which is not a collinear member, which is not either along AB or AC, it is a third member. Now what can we say? And there is no external force acting on AD. So now this is on point A. So no external force on A. What can you say about the force on AD? Force on AD has to be 0. Is that clear? That follows from the previous logic. Suppose there was another member here which is in line with AD. Now that member is not there, that means that is exerting a 0 force. So if that is exerting a 0 force, then force in AD must also be 0. So therefore, this can be another rule saying, and that if there are two collinear members connected to a third member which is not collinear and no external force acts on the joint, then the force in the non-collinear third member has got to be 0. And so this is what we sometimes also refer to as, so force in AD is equal to 0. Such members where forces are 0, we call them as, sometimes we give a name, 0 force member. Okay. Now another special case comes here is if we have two non-collinear members AB and AC and there is no external force on pin A. What can you say about force in AB and force in AC? Both of them have to be 0, because you could imagine AB is connected to another 0 force member which is in the same line. Similarly, AC is connected to another 0 force member which is in the same line. So therefore, in this case, when we have two non-collinear members connected to a pin, to a joint, and no external force on the joint, this implies each member is 0 force. But notice this will work only if there are two members. If there are three, this will not work. Okay. So these are some cases where we can, just by looking at these things, we can say if the forces are zero force or not. And these are what have been explained here by realistic choices. But let's look at a case like this. Let's look at the bottom right hand part. We have shown a truss. I think I had shown this in the last class also. Now given a loading like this, can we, by inspection, can we tell which of these members are zero force members? So let's start from this end. A is not a zero force member. We come to pin C. CA and CE are collinear. They are connected to CB. CB is not collinear. So if I look at this pin, what deduction can I make about BC? BC has to be zero force. Now you can't make this deduction if you look at BC from pin B. But if you look at BC from pin C, you can easily make this deduction that here BC is a zero force member. Okay. Now I go to pin E. Can I make any such deduction? No. Why? Because I have 4 members and they are not collinear, so I can't. I go to point D, to the pin D, or let's go to the pin B. This member is 0, so I can remove this. But then I have BA, BE, and there is an external force. So therefore, what I can, only thing which I can get here is these two are there, BE is there. So that means the force in BE I can directly work, that must be equal to this 25 kilonewton, the component of that along BE. So I can get the value of the force in BE. It will be 25 cosine alpha, where alpha is the angle between the 25 kilonewton force and BE. Whatever, 25 upon cosine alpha, so you will be able to get that force. Okay. Now when I go to pin D, this is an externally loaded pin. There are 1, 2, 3, 4 members in addition to the external force. So I cannot make any simplification from here. I go to pin E. On pin E I have these two. I know this force, therefore I should be able to, no, still I will not be able to make any deductions. I will have to then work out. I know one of these, there are still 3 pins, I can't get any more because I will be able to solve only for 2 unknowns. I go to G, I can't make any simplification. At F, I can't make the simplification I talked about because there are 3 members at F. If there were only 2, if FG was a zero force member or FG was not there, then these two would have also become 0 based on the third logic. But since FG is there, we cannot do anything. We can't do anything here. Let's come to this pin K. What can we say here? Kj will be zero force. If Kj is zero force, then I go to the pin at J. What can I say? Ij will also be zero force. Because this is zero force, then we have these two connected to a third member. So therefore the third non-collinear member will also be 0. So therefore Kj and Ji are also zero force. Kj is zero force member, and so therefore then Ji is also zero force member. So some of these simplifications we can get without doing any calculation. Sometimes you may be asked some of these problems, identify zero force members by inspection. So this is how you will do that. Now I want to talk about how these simple designs, sometimes if you don't take these into account, how they can cause problems. If you go and do a Google search on Hyatt Regency failure, so Hyatt Regency failure, it will probably come there. In 1940s, I think this was a hotel in Michigan, Hyatt Regency, where they had designed a walkway, and this walkway looks like this, that there were, next to the building there is a small balcony which was jutting out, that was the 4th floor, this is the 2nd floor. And the design was that they had made these two balconies this was the schematic walkway of the bridges which was spanning in the hotel, that there are these two things coming out. Now what happened was that there was some dance or something, some celebrations going on in the ground floor, and a lot of people had gathered on the two balconies. And suddenly this structure where the people were standing, it collapsed. There were about 114 people who died. Now of course if it was India, this would not have made such a big hue and cry, but 114 people dying in a country like the US was big this thing, and there are a lot of this thing was a lot of analysis was done, and it turned out that basically simple mechanics principles were not followed, or there was a slight deviation in design which the designers made, and they thought they were doing something, they were creating a stronger structure, and actually in turn it turned out that they were creating a weaker structure. What happened was, let's show it to you. The original design is shown on the right, which basically went from top to the bottom. There was a single column, and this column was bolted here at these two ends, and what was going from top to the bottom was a single shaft which was holding the support to the walkways. Now when they were building this, they thought that making such a long shaft, long column or long bolt would be difficult or would not be practical, so they divided this into two parts. From the top of the roof to the 4th floor, they put one shaft which was bolted here, and another shaft was put from 4th floor down to the 2nd floor, which was bolted at the two ends. So this is how the original design was: one full long column which was bolted here to the sides, and as it was built, it was replaced by two columns, and let me show that in a schematic way. So this was supposed to be the original design. This was the walkway on the 4th floor, walkway on the 2nd floor, and connected like this, and there were supposed to be bolts here and bolts here. And if we analyze the original design, suppose if there is weight W on the 4th floor and weight W on the 2nd floor, then if I draw the free body diagram, what I find is, because there is weight W here, W by 2 and W by 2 will come on the two parts here, and so each of these two bolts which are there, or if there is more bolt, then they have to take a load of W by 2. On each side, the bolts had to take a load of W by 2, and similarly on these two sides at the 2nd floor, the bolts had to take a load of W by 2. Okay, so that means if there are 4 bolts, the total weight is 2W. W by 2 gets split on all 4 bolts. Now we look at the modified design. In the modified design, what was done was that these two things were hanging from the top. You put 2 bolts here, and then this basically, which was a single structure, is now split into 2, and then you have this one with 2 bolts here and this one with 2 bolts here. Now let's do a simple free body diagram analysis of this. Let's look at this bottom structure. There's a weight W coming on the walkway, so each of these loads get a load of W by 2. We draw the free body diagram of the 2 columns here, which are these intermediate columns. There's a load of W by 2, so load of W by 2 and W by 2 comes like this, and there is a load of W which is coming here. So now when I draw the free body diagram of the 2 columns, there are 2 half columns which are outermost, then there's a W by 2, there's a W by 2. So that means the load on each of these columns which are there, 2 half columns, is W. So that means effectively the load which is coming is W by 2, W by 2, W by 2 and W by 2 on the 4 bolts, but on the 2 outer bolts the load coming is W. And what they did was they didn't do this analysis and they kept the same bolts. So they kept all the bolts with W by 2 force capacity, whereas in these two bolts the load which was coming was W, so therefore these bolts failed, and once they failed the whole structure failed. And that is what caused to the big, and a simple, what they thought that they are doing something good by reducing a column of length, such a big length, to 2 half-length columns, but not doing a proper free body diagram and proper statics analysis led to the failure of this. So this is, I have made a very simple analysis. Of course, when bolts fail we talk of shear failure, and these loads they cause shear stress in the bolts, that I am not discussing here. Now we are almost at the end of the section on trusses, but there are some more problems which are there, and which is what we call as frames. That means in a truss we did an analysis, each member was a 2-force member. Now there may be some more problems where the problems may be consisting of members which are not 2-force members, and we have seen some of these in our problem already, but we have seen them as single body member or single component. If there are more components, then what we have to realize is, for example, here we have shown this member AD, which is a straight member. It is connected to CEF, which is another straight member, and then there is BE, which is a single member. There is a cord DE, which is tying, and there is a weight. Now here if we look at, when we analyze, we call all these things as frames or machines. There are more than one members. Now to find the reactions overall, first thing we do is we draw a free body diagram of the entire structure. When we draw the free body diagram of the entire structure, if I draw the free body diagram of this, then I will not show any internal forces. So for example, when I draw the free body diagram, at A I will get AX and AY, there is a pin, and there is this the string which is holding it at CD, so I show a tension at CD and the weight W. All other forces are internal forces. Now having done this, I may be able to solve for some of the reactions, or I may not be able to solve, depending on the type of problem it is. So here if I take moments about A is equal to 0, I will get T. I do sigma Fx is equal to 0, sigma Fy is equal to 0, I will be able to get Ax and Ay. Next, suppose if I have to find the forces in each of these members at each of the pins. So then I start doing an analysis of the frame. In this frame what I realize is BE is a 2-force member. If I assume that all weights are negligible, then BE is a 2-force member. So that means the force along BE, this we have already discussed, will be along the line of BE. So when I draw the free body diagram of the straight member AD or ABCD, then what I will have is, at point D I will have a tension, at point C there is a pin, so I will have CX and CY. At point B I will have just a single force BE, which is acting along the line of action of BE, because BE is a 2-force member, and then at A I will have AX and AY. Now I have already solved for Ax and Ay from the overall free body diagram. So now I do a counting. I have 3 unknowns and 3 equations. So I should be able to solve for Cx, Cy and Be. These 3 I should be able to solve. Now the next key step in these problems is, if I draw the free body diagram of Cf, then if I have shown this as Cx and Cy, then the forces at C will be opposite. It will be minus Cx and minus Cy, and I have already found these out. I have already found out Be, so then all I have is F here, and actually what it should lead to is, I have already solved all the forces. So it should verify when I do my equations. If I write the equations for the link CEF, then I should get everything should be in place. That means whatever unknowns I get, I should get 0 is equal to 0. If I take moments about point E is equal to 0, it should turn out to be like that if my calculations are correct. So that is how you can solve for problems like this. So no, you either assume it to be tensile or compressive. Unknown force, it is up to you. So here I think in the book he has assumed it to be compressive. You could assume it to be tensile. Once you solve for it and you know the correct direction, then you put the correct direction. So this is your own, this thing you can show it in any direction you feel like. But again you realize, if I use the fact that BE is a two force member, that will simplify my calculations. Otherwise I have to draw a free body diagram for BE also. So when we have a multi-component frame, try to see things which you can make from these, because you may have to break the frame into parts to be able to solve for this. So next, well, there's a similar problem, problem 6.4 solved in the book, which is basically, it says members ACE. So we have an L-shaped member ACE, which is one member, A to C to E, and BCD, the other one is not L-shaped, it's with a slant angle. BC is one member, BCD is another member. So these two are pinned at point C. Okay, and then there is a link D is also connecting these. Now a force of 480 newtons is acting on CD at the given location, and then at A we have a pin joint, at E, at B there is a roller. So what does a roller mean? The force will be only in the horizontal direction, because in the vertical direction at B it can move. So therefore the force will be only in the horizontal direction. So the unknowns will be AX, AY and BX. So first, if I draw the free body diagram of the full truss, I should be of the full this thing, I should be able to solve for the three unknowns. Now next, if I have to find, it says determine the force in the link DE and the component of force exerted at C on member BCD. So we have to find how much force the pin C is exerting on BCD. So now DE if I have to find, so what I will next do is draw the free body diagram of BCD. I know the force at BX, at C I will show two unknowns CX and CY, and at D I will show a single force in the direction of DE, because DE is a two force member. So that means then notionally I count in my head, I have three unknowns and I have three equations, so I should be able to solve directly. So that is how I will, so before you solve or before you proceed for the solution, solve the problem, look at the problem in your mind, decide your strategy how you will solve it, and then you go ahead and then you just implement the strategy. And so this is how you will solve the problem. You first solve for the total reactions which are there, you solve for reactions AX, AY and B, and again you can look at the details in your textbook, and once you have this, then you can draw the free body diagram of one of the links, and you can, so this is for the check, so actually this was not needed. Then as I said, we draw the free body diagram of the link BCD, and there I should be able to solve for all the unknowns. If I draw the third free body diagram, that would just act as a check. You don't need to do that, but if you have the time, and if you, in the exam of course you'll never get the time, but otherwise you can, it's always, if you draw the free body diagram of the third link, then things should check out. You don't need to draw this free body diagram because all these forces are already known to you. The last thing, in some of these, there may be some problems like this where you have to find the force F is being applied on a cutter on the two ends, and the effect of that is to get a squeezing force on Q. Now if the force F is given and the geometry of the cutter is given, and you are asked to find the force at Q, then in problems like this, if we have two links connected, we draw one half of the body, either the top or the bottom, and there is symmetry. This we have to realize in the problem, there is symmetry. So now when I draw the free body diagram of this link, I have the force F here, there is a pin at A. So at the pin I will get AX and AY as two unknowns, and if it is given it's frictionless, which it is given in this problem, then at Q you will get only a vertical force. So given these, now you have to, given P, you have to find Q. What is the easiest way? Take moments about A is equal to 0. So you will get P multiplied by this distance must be equal to Q multiplied by B. So you will get the force at Q. So sometimes the overall problem may look complicated, but when you break it into components and draw the free body diagram of each component, then you should be able to solve the problem in a relatively easy way. Maybe at times you may see some of these connected with a 2-force member. So there you remove that link where the 2-force member is there, put a single force there if it's a 2-force member. So things like this, you have to look for simplifications in the actual problem, and then you should be able to solve any problem which is solvable. Of course, there may be statically indeterminate problems which you cannot solve. So those you cannot solve, but others you will be able to solve. Okay, thank you. So now, when do we meet? Tomorrow? Tomorrow or tomorrow we are meeting, or Tuesday, na? So tomorrow at 5 o'clock we have an extra class in this room itself. This room is free, so we'll meet at 5 o'clock here. Okay, and this is to make up for the last